would like to hand over to our first keynote speaker. He was so nice to come here. And Nicolas Wu will tell us something about modular higher order effects. The stage is yours. Thank you.
Great, thank you very much for the invitation. And good morning to everybody here. It's a nice, cozy room. So hopefully, without too much mic assistance, you'll hear me at the back. So I'm here to present higher order effects. This is really work that has been going on for quite a few years. So let me introduce you to, well, first of all, we're in the UK, which is well known for its literature and its, great writings. And so there are some characters that my children really like that I want to introduce to you. So first of all, there's this fellow here, which all children in the UK know. His name is Mr. Hoppy. And then there's this little fellow here, and his name is Alfie. Now, this is part of a book called SEO Trot by Roald Dahl, which is a great favorite. And SEO Trot is a strange title, and it refers to some text that happens in the book, which is indicative of how great Britain is at writing stuff. It goes something like this. SEO Trot, tag Regib, emok, no SEO Trot, which is complete nonsense. Why this nonsense? Because Mr. Hoppy is trying to make Alfie the tortoise crow quickly, and the trick is to talk backwards and all in capitals. So what he's really saying is something like, tortoise, tortoise, get bigger, get bigger. And so how can we help him to achieve this? Well, we can use modular higher order effects. Okay, so what we're going to do is we're going to teach him a little bit of code. So Mr. Hoppy really wants to write something like this. He wants to say, hello, Alfie. He wants to say something to the tortoise. He wants to say, get bigger. And then he's going to say goodbye. So in this piece of code, what we see is that there are various operations that construct the program itself. So we have several tell operations, and they are all there basically to do something with this code. And then what we want as well is a way of indicating which parts of this conversation we want to have backwards and in capitals. So a priori will make sure that hello Alfie is not in capitals and goodbye, hello Alfie and goodbye are just normal, and it's the stuff in the middle that will be backwards and in capitals. So to do that, we're going to have this censoring, and we're going to censor backwards the text inside these brackets. So there's a bit too much lag for this to work. Okay, so we're going to do backwards tortoise, which is going to give us the SEO trot. And then furthermore, we can censor something within that context so that we get in capitals and backwards the get bigger, which corresponds to the tag regib of that text. Okay, and because this is an example of what we call effects handlers, we're going to have a handle function here which handles away this program using two things called handlers, where censors deals with the censoring and the writer handler deals with the tell operation. Okay, so the way that the rest of this talk is going to unfold is I'm going to try and focus on the different parts of the title. So we've got modular higher order effects. So effects up here in red are the key thing that we're trying to deal with. And the point that I'm trying to make here is that there's this distinction between the pure return value, which is unit in this case, and the tell and censor effects, which is the bulk of this code. So the pure part really just corresponds to the return, and then the rest of it is the actual part that does effectful computation. And the reason that we're focusing on modularity, so we're talking about modular higher order effects, is because there are two different kinds of modularity at play in this program. First of all, we've got tell operations and censor operations. And so you can think of those as being two small languages, a language that just knows how to tell and a language that just knows how to censor, and we're combining both of these things into a single language. So that's syntactic modularity, where the syntax of the two languages are able to combine into a single place. So that's tell and censor combined together. But there's also something that we like to call semantic modularity. So semantic modularity says that the models of smaller languages can be combined into a larger one. So the censors handler deals just with censors, and the writer handler deals just with tell, and the combination of the two deals with the whole program. So that's why we have what we call semantic modularity. Okay, and the reason that we call this higher order is because there's this distinction between what we call the first order effects, which are programs, oh, my slides have disappeared, which are things like tell, Where tell and other operations like this are simple and might contain parameters, and more complex higher order effects, which may contain parameters just like the first order ones, but also contain programs as one of their parameters. And that's the thing that distinguishes them from first order effects. So here we've got the body of this contained within the sensor itself. And of course, we could have some nested programs as well. Okay, so that's going to be roughly the structure of my talk. I'm going to focus on these three parts of the title. And so I'm going to just start with effects, by which we mean side effects, which are something that we'd normally like to avoid. Let's think about where these come from. So this program that we've just seen seems quite innocent, and what I want to do is a sort of a deep dive into the history as to where this program comes from and what the aspects are that we need to get there. So there are things like the tell and sensor effects in play. We've got pure values. And to understand where this sort of interplay between operations and effects and pure values go, we have to go quite a long way back in the history of CS, probably right back to the beginning. And this is a brief history of programming languages. Here is the ALGOL committee all putting their hands up, apparently for the first time in agreement on something. And what they agreed on was the question, do you agree to have your picture taken? And then they all agreed. And apart from that, the committee never agreed on anything else. So this very big diagram, you're not expected to see it in any detail, outlines just the development of programming languages to 1971 from 1952. So I've got no chance of doing a proper history here, and it will be largely opinionated, and there will be mistakes, for which I apologize, but hopefully it gives you some idea of where things came from. So let's start with ALGOL in 58. The revised algorithmic language came out in 1960. It was the result of a committee of people, its code looks something like this, which is very familiar because it looks a lot like imperative languages that we have today. In fact, it brought many, many different innovations to the world, and Tony Hoare at the time said this was a language so far ahead of its time that it was not only an improvement on its predecessors, but on nearly all its successors, and that was in 74. So what did it innovate? Well, we have code blocks and lexical scope, nested procedures, procedure passing, call by value and call by name, and of course BNF. So lots of different things came out of this particular piece of work. But also came a mention of side effects for the first time. Actually, not quite the first time. Side effects, apparently, according to the OED, first were talked about in 1814 in the monthly repository of theology and general literature, where side effects are considered to be, one way of describing evil things, where God has in mind like the stuff that he intends, and then when bad things happen, well, those are the side effects, according to the literature. So side effects have been related to evil things for a long, long time. And the earliest trace I can find of the mention of side effects goes back to 1960 by Woodger, who says something like, it's unreasonable to allow the evaluation of expressions to include side effects. So from the beginning, it was understood that really they're nothing to do with what we want to compute in our results. And not long after, two of his colleagues, so Samuelson and Bauer, they agree, in fact, they're a bit more emphatic. They say the idea of expressions having any effect but defining an actual value is so preposterous that it was not even considered by the ALGOL committee. So right from the beginning of even an imperative language, side effects should be ruled out from the start. And we see this happen a little bit more strongly again in 77 when Backus does his keynote at the ACM in receiving the Turing Award, and he says that the world can be split into two places once you've got an assignment statement. The things to the right of the assignment statement, which are the pure expressions, which is sort of a nice world, and the things to the left of the assignment itself, which is a disorderly and chaotic world that we want to avoid. And he says that the properties are often, the nice reasoning properties are destroyed by side effects. So he's trying to escape from von Neumann machines. And he goes on to say that what we really want are things like denotational and axiomatic semantics. And so, although it seems like we're left thinking that in an imperative world there's no hope, what we'd like is to see that maybe there's going to be a denotational semantics for the imperative world, and maybe there we'll see some reasoning principles come back in. So how do we get to denotational semantics for imperative languages? Well, I think the beginning is somewhere to do with the relationship between ALGOL and the lambda calculus. This is work by Landon in 1964, where he introduces the so-called SECD machine. And what he's trying to do is build a correspondence between this language that he calls the applicative expressions language, which is very much like Haskell with lets rather than wheres, and the lambda calculus. So he has this correspondence between the two. And he gives an operational semantics of the SECD machine in this paper. A little later, so 1 year later in 1965, he then extends the applicative expressions to be imperative applicative expressions, where he adds the assignment operation. And then he gives a semantics of algol in terms of these imperative applicative expressions. And so what we're seeing here is an early version of denotational semantics, because he's mapping the meaning of algol to the meaning of something like the lambda calculus, and that correspondence is how he gives the semantics. So this is the first trace, I think, of denotational semantics happening in around 1965. A little bit later again, Landon writes in 66 this really famous paper called The Next 700 Programming Languages, and he advocates what we call denotative programming as a methodology. So he's unhappy with this distinction between imperative versus, well, everything else, where everything else is called things like declarative or functional or maybe logical programming. He thinks there should be a word that kind of encapsulates all of the other things that aren't imperative into one place. And for him, he thinks denotative is the right expression to use. And so his description of what denotative means really foreshadows the development of what we would consider formal denotational semantics now. So those semantics came up a little bit later in 71 by Scott and Strachey. And the description of Peter Landon looks something like this. He says that, this is the first sort of denotational semantic given in the paper by Scott and Strachey. And what Landon is saying is that each expression has a nesting sub-expression structure. So this is an expression that we're trying to evaluate. It's v0 plus v1, and we've got some sub-expressions v0 and v1. And then he says each sub-expression denotes something, which we can think of as the denotation of these two subparts. And then finally he talks about the thing that the expression denotes. The value of this whole thing is the combination of these parts over here. So he's, in words, really described almost exactly what Scott and Strachey came up with later on. Okay, we're trying to think about how we get from denotational semantics all the way to a kind of denotational understanding of effects. And we get that, I think, for the first time in terms of monads, and let's think about how that came about. So we've got monads and the lambda calculus coming up first. So Dana Scott thinks about the lambda calculus in terms of category theory in 1980. He thinks that the theory of pure functions is category theory itself, so he describes this in this paper on relating theories of the lambda calculus in 1980. And he thinks that the category theory is the right way of doing these things. A little bit later, Eugenio Moggi picks up the view that monads should, or he in fact realizes that monads give a good denotation of semantics computations in this paper called The Computational Lambda Calculus and Monads. And he's trying to understand the lambda calculus where you extend it with various effects. So he builds on the work of Strachey, and it's hard to see here, but he basically introduces lots of the different monads that we would understand today. So that's things like state and exceptions, and a whole bunch of others are all introduced in that original paper. And then a bit later on in 91, it's more than the lambda calculus. He's actually thinking of monads as a means of describing computation directly. So we have partiality, non-determinant side effects, exceptions, continuations, and I/O, all described in that really early paper. That's more from the theoretical perspective. How do we get that from there to the practical perspective? A slightly different story. So in 85, Phil Wadler thinks about exceptions and how we can have a theory of exceptions in Haskell. And he starts by using lists and laziness to deal with exceptions. But not monads. So at that point, I think he's unaware of that work. And a little bit later, so in 88, but then the paper's accepted in 90, Spivey picks up this idea of exceptions, and he realizes it's connected to the category theory that Moggi was talking about, and he introduces the maybe monad, actually called maybe, and with just and nothing constructors, so he's the person that invented those terms. And he also talks about return, join, and bind, or Kleisli composition, all in that early paper. So he really is the person that realized that functional programming could be assisted with monads. Modular picks up on this idea and introduces comprehension notation for monads in 1990, and does a really great job of making monads come to life between sort of 1990 and 92 with a whole bunch of really useful examples. So interpreters, error messages, state, output, and all sorts of different things, so non-determinism, and even an example which he says is contrived and John Hughes discovered it, and he doesn't really know what you can do with it. So he thinks that there are all sorts of different examples that you can do with monads, and I think it's this work that sort of set it in stone for the Haskell community. So I've just done a grand tour of how we got from this imperative piece of code to a kind of functional understanding of it in terms of monads. And what we can see in this piece of code is that we have an annotation at the type level of the kinds of effects that we would expect this program to use. So it uses tell and it uses censor. And that's an indication of the effects that we're going to have in the system. But actually, that has nothing to do with monads a priori. So in '86, there was this paper about integrating functional and imperative programming that talks about a type system where exactly this mechanism is in place, but it has nothing to do with monads, right? It's just saying there are various effects in play, and we can annotate these at the type level. It takes quite some time before the relationship to monads was established. In fact, it took something like 10 years. And it was, again, Modular who did it, and he himself puts it really well. He said that, half a day, he says, goodness knows why it took so long, because the correspondence between effects and monads turns out to be surprisingly close. So I think the point that I'm trying to make here is the state of the art comprises many small steps where the obvious might be right in front of you, but it could take a long time before that's discovered by the community. And what I'm observing here is, over the period of many years, lots and lots of small contributions all leading towards a much larger picture. In any case, I want to just focus still more on this simple program and talk about monadic do notation and the origins of that. So the do notation itself was conceived by Launchbury in a paper in '94 called Lazy Imperative Programming, where he doesn't use the do keyword at all. So he just uses curly braces and semicolons. And actually, I think the code looks a lot cleaner, and it looks more imperative, which I think is the intention. And so the syntax looks something like this. You can't really see it, but the point is that you have curly braces rather than indentation. That's implemented in '94 by Mark Jones, and that's where, for lexicographic reasons, he introduces the do notation as a do keyword, so it just makes things easy to parse. So we can also think of this as a syntactic sugar for monadic operations. So de-sugar from this program into something that uses the bind and return of the monad. And while we're at it, the word syntactic sugar was coined by Landin in one of the papers that we've seen already. So that was coined by him in '64, where he said, we're going to use a syntactic sugaring from applicative expressions to the lambda calculus. But not just that. The indentation sensitivity that we're using in this piece of code was also due to him in that same paper. So this guy really came up with all kinds of interesting ideas in a very short period of time. Okay. How are we doing? Right, so I want to talk about modular effects now. So what is it that we mean by modularity in this world? So by modularity, there are two kinds of modularity in play going on in this program. So this is the program that we've seen, and these are the handlers that give us semantics to that program. We have something called syntactic modularity, and then we have semantic modularity, which I've described briefly. So syntactic modularity is where the two languages can be combined into one. And so that's where we have sort of the tell and the censor interplaying in a single program, where you can think of these as individual sublanguages. And models of smaller languages can be combined into a larger one. So that's where censor deals with the censoring and Python deals with tell. Let's focus a bit more on the origins of syntactic modularity and where that comes from. So for us, syntactic modularity is the combination of two things. Combining what we call initial algebras with coproducts and using a class system to constrain the types. So that tends to be the way that we Haskellers do things and what's done in the library that I'm presenting here. And this is often called the a la carte approach, which was due to Baptista in 2008, who really popularized this idea of using syntax from syntax trees defined as free monads, and then combining these things using type classes. Now, the reduction of a syntax tree is done by using an algebra. And I want to just dig a little bit into where the idea of algebras came from. This is very related to something that Tim Sheard had in mind previously in 2001, where he wanted to reduce things using catamorphisms. And catamorphisms, the history of that is quite long, and I'm not going to go into it too far, but I think the start is roughly in 1968, where Birstall starts thinking about proving properties of programs by structural induction. And that's the first time that we see structural induction playing with programs directly. In 75, Tony Hall goes a bit further and starts talking about recursive data structures in more detail, thinking about why you don't want to have pointer algorithms in play, but rather it's better to have an abstraction over the pointers themselves. You don't want to be thinking about memory spaces, you want to be thinking about abstract notions of data instead. And in 77, we start seeing the adoption of category theory to give a semantics to these kinds of things. So how do we give semantics to trees? How do we reduce these? That's due to Gogu and Thatcher, Wagner and Wright, who started this Bourbaki-style group where they were writing under a pseudonym. They were called the ADJ group for junctions, which is a categorical concept. And they think about what we call initial algebra semantics. So starting with what we call a syntax tree, that's an initial algebra, and then how a semantics to that is given by something called the unique homomorphism, which just says that there's a canonical way of reducing syntax, and that's something that they observe in around 77. You'll hear in the Haskell community this excitement of this word called catamorphisms, which really appears only in that subclave. So nobody else really knows what a catamorphism is, and most Haskells themselves don't know what catamorphisms are, I think. But the story of that starts with the so-called Bird-Mertens formalism, which is often called squiggle, which is a joke on algol because they had lots of squiggly letters in their rendition of these things. Bird was thinking about a theory for lists. Mertens was thinking about a theory for rose trees in around the late 80s. And Mertens dubs the word catamorphism as the unique homomorphism that breaks down the constructors of a tree using an algebra. The word is Greek, so kata means to destroy or to go down, as in catastrophic. And so he uses in his paper, he insists that whenever you describe a catamorphism, you have to use the letter H, because that stands for catamorphism, and he scribbles it out and writes, it stands for homomorphism. But that's kind of the joke that he plays on us. The work by Bird and Mertens isn't originally categorical, so it's purely equational to start with. And it's in 1990 that Grant Malcolm picks up on these ideas and goes, hang on a minute, this is related to all the category theory that the ADJ group have been playing with. And so he puts it into a categorical footing. And then the idea seems to explode in 91, where you've got this famous paper called Functional Programming with Bananas, Lenses, Envelopes, and Barbed Wire. And that describes that there's not just catamorphisms, but in fact a whole family of different morphisms with confusing names that can be used to reduce programs in all sorts of interesting ways. So the problem with that actually is that every time a new morphism comes up, so there are loads I can think of, there's like the mutumorphism, the anamorphism, the zygomorphism, then the histomorphic prepomorphism, all sorts of combinations of these things. And who knows what they even mean? Well, it takes a long time to figure out all these definitions. What was missing was a way of unifying all of these into a single framework. And that took a really long time. So in 2015, Hintze, Wu, and Gibbons came up with a kind of a way of unifying all of the prior work into a single thing called the conjugate hylomorphism, which we named the mammamorphism for short, because it's the mother of all recursion schemes. So that is, I think, where we are in terms of the catamorphic story. And the take-home really is that we use what's called an algebra to reduce a syntactic functor, which basically says that there's a way of reducing syntax down in a very structured way. Okay, so what does that mean for our library? So it means that things like the get and put operations can be described by a syntactic functor. It looks something like this. It says that we have a put operation, we have a get operation, and these things are functors that take in some state and take in some continuation that says where the rest of the program goes. And so syntactic modularity means that these two separate functors can be combined using what we call a coproduct into the tree itself to have a single tree that contains both of these operations. And we do that by injecting into something called the prog monad, which is basically just the free monad, using the a la carte approach to do that injection. Okay, and the semantics for these things is given as an algebra. I don't want to go into the details, but roughly speaking, we're reducing puts in terms of the state transformer, for those of you who knows what that is. Okay, so much for syntactic modularity. I also said that I would say something about what we call semantic modularity, so where models of smaller languages can be combined into larger ones. And for some of you, the question might be, hang on a minute, what is a model? What do you mean exactly by that? So for that, we go back to our friend Landon again. So he didn't quite invent models, but in the Next 700 Programming Languages paper, his idea was that there are 700 languages because what you want in programming language design is a core language, which he calls ISWIM, which stands for If You See What I Mean. And that language should be extended with lots of small domain-specific languages, each for its particular use. So he thinks that these DSLs are what he calls the primitives of the domains that we're interested in. So that's in 66. And so he saw that the main language should be comprised of 4 different parts. So there's the sub-expression, or 4 different groups of laws. So something to do with sub-expressions that says that if 2 terms are equal, then they should be equal under sub-expressions. He also wants definitions to have equality constraints on them that says that you can have definitions as let or as where, so he thinks that there should be multiple ways of defining different things. That built-in expressions like conditionals should also obey various laws. And then finally, he thinks that the primitives, that is to say, the user-defined DSLs, should also obey whatever laws the user wants. So way back here, we're already seeing an understanding that we want domain-specific languages to be subject to a bunch of laws that describe how things should interact. Okay, so equations are things that should be maintained right from the beginning. In today's language, we might call these equations theories, and particular instances of this theory is what we would call a model. So that's where the idea of models comes from, at least in CS. And so we have things like theories for monads. So the theory for monads says that we've got this interface, which is going to be the return and the bind operation. And the monad laws are things that we can understand as the theory that supports how monads should interact. And Gibbons and Hinter have a nice paper that talks about how you can use the do notation as the way of explaining those theories. And so for us, where we're talking about things like, when we're talking about get and put operations, it means we want theories like this, that say putting and putting again is the same as putting the second time. If you put then get, then that's the same as just putting and then returning the thing that you put. And then if you get then put, that doesn't do anything. So these laws you can think of as the theories, and there should be multiple models of these theories. For example, the standard model is to understand state as a function from input to output, fine. But maybe you want it to be a function from input to output, but that also records the number of times something was put. So that could be some extra data that exists on the side. It still satisfies the laws, but it's not the, I'm getting a no.
The last law is tricky with that one.
Okay, that's true, yes. I'm thinking of timing information. Okay, fine. There are other models of this that we use, and as in the effect handlers world, we do use these. But that's a good point. Thanks for picking up. So this is an old idea that's really refined over time. Yeah, that is a good point. The laws of programming for things like get and put also go back quite a long way. In fact, they go back all the way to 1964 in a relatively hard-to-find thesis by Igarashi. It took me quite some time to pin this one down. That was picked up by De Backer, who talks about how assignment should work, very much in the way of the put-get laws that we described in 66. And then there's this big paper in 87 which describes the laws of programming. And I find this note that they have here. They say, some computer scientists have abandoned the search of rational laws to govern conventional procedural programming, and they tend to recommend the use of functional programming or logic programming as alternatives. But here, we substantiate the claim that conventional procedural programs are mathematical expressions subject to laws. So this is where they kind of try to pin down a way of being reasonable with imperative programs. From the more categorical perspective, we see this coming together in the work of Plotkin and Power. So they think of the notions of competition as determining monads. So the idea there is that you have operations, and you have theories over those operations, and from there you can define or you can derive the monads, and that connects back to Loubet theories, but I won't go into that history. Sometime later, Plotkin and Pretnar use these ideas, and they think of handlers as being a particular model for an algebraic theory. So that means handlers are an instance of the theory. So different handlers will be different ways of dealing with that, an operation and its, the respects its laws. And they observe that operations and handlers are dual. Operations construct effects, and handlers deconstruct effects. So what's a model? A model is an instance of an algebraic theory, and we implement that as a handler. Okay. And so here is the handler for put and get. So we have the state handler. And what we do when we apply the state handler is we say something like handle with the state starting off as hello, whatever program you want, and then that will execute that program in some way. And the point is that the handler itself has several components. There's a list of what we call the input effects, which describe the effects that this handler will consume. So what are the syntactic fragments that will get destroyed or used up by this handler? Then there's a list of what we call the output effects. So what are the effects that will get produced by this handler? So some handlers will destroy things, others will create new effects to be handled later on. And then finally, there's this thing called the result wrapper. And the result wrapper is basically going to transform your pure values by wrapping them around some functor, which adds information as you process through. So I know this is too soon after Christmas, but here is an analogy of what these handlers are actually like. They're like one of these things. And if you don't know what these things are, it's a kind of large tube where you put a Christmas tree in on one side, and what comes out on the other side is a Christmas tree wrapped tightly so you can bring it home, okay? And I've seen some fun pictures on the internet that I didn't dare reproduce of a lady who decided to jump through one of these. And she ends up sort of on the floor holding her Christmas tree tied together. So that's what this machine is for. So you can think of this state thing as being like one of these machines. So let's try and understand why that is, okay? So here is this machine that takes in trees and does something to those trees. So I've already said that we have input effects that get consumed by this handler. So here is our tree. It's a syntax tree which has things like get and put in it. And we can see that the signature of this is we're using get and put, and the pure value it returns is A, which I'm annotating here at the base of the tree. Okay? Now, this goes through the machine, and then on the other side of this machine, you'll notice that the effects have all been removed by the handler itself. Okay, so something happens to the tree. And what we're also seeing is that the pure effect has changed. And so what we should annotate this program with as well is not just that there are no output effects, but also that the result wrapper is this S cross blank, which comes from here. And so this pure A passes through this part here, and then gets adorned with this extra state information. So two things happen. One, the tree goes through the machine, stuff happens to the effects, things get removed and things maybe get added, but the pure value also goes through, and then it changes so that we have a different pure value at the end. And these two things combined are what I would say is how an effect handler interacts. Okay? So that's a sort of a sketch of how these things work. And when we talk about semantic modularity, we want to say that different handlers can be different sort of models of the underlying theory. So here we have one that does censoring the text that we had with the hello Alfie and the su tag. And here's a different handler for the same program that uncensors things. So it gives you back the original clear text so you can read what was going on in the first place. And the point is that the program, the Hoppy program that we had right at the beginning of this talk, hasn't changed, but the handlers that we're applying to it have changed, and so the output of the program, the semantic interpretation of the program, is modified. Okay, and shameless plug, the models of these things typically have equations attached to them. In Haskell, we have no way of asserting, or at least checking and verifying that those equations hold true statically. But we have a paper that does this in AGDA, which you can see at PADL tomorrow, no, on Wednesday, that Zishan will be presenting. So go along to that if you want to know more about how we can do these things. Anyway, semantic modularity allows models to combine. And what I mean by that is that in this example where we have sensors and writer working on this tree, there were two different handlers at play. There's the sensors handler and there's the writer handler. And these two things have very different signatures. So on the one hand, what the sensors is doing is it's taking tell and sensor operations and it's emitting tell operations. And on the other side, we've got the writer handler, which takes tell and emits nothing. Notice that the pure values are untouched by the sensors, but the pure values are crossed with W in the case of writer. So what we really want to do is we want to take these two handlers and we want to fuse them together to make a different handler that combines all of these interacting components together. So we can take these two handlers, fuse them together, and consider this to be a single tree transformer that goes from one side to the other. I'll spare you the Christmas trees, but what we can do is we can start with a program with tell and sensor effects, and the output's pure values of type A. We can pass it through the first part to remove the sensors and just have tell of A, and then we can pass it through the writer effect, have that should be empty, and then just W cross A at the end. So there's a way of removing effects as we work through this. And that was done by the combination of handlers, which we call the fusion of handlers. So now it's the last part of the talk where I want to talk about higher order effects. Well, what I want to distinguish are the first order effects, which are the things that are simple operations that may contain parameters. So the first order effects are really the first ones that were studied by Plotkin and Pretnar and Plotkin and Power, sorry, and they obey the algebraicity law. The algebraicity law says something like this. It says, if you have an operation with n parameters, and you can think of these parameters as programs or continuations, and then you continue with some continuation k, then that's the same as adding that continuation k to the end of each of these programs. So for example, if you throw followed by k, that's the same as throw, because throw destroys the rest of your program. If you have or, which is like a non-deterministic choice between n different programs and then continue with k, that's the same as having or, where each one of those programs is continued with k. If you have, that's repetition, if you have put, which continues with p and then by k, that's the same as continuing in the p parameter, and with get, it's the same idea. So note that this is a slightly different rendition of put and get, the ones I had earlier on, where I'm explicitly telling you which program continues after these things. And that's the key insight to why these things are algebraic in the first place. These laws, or the algebraicity law, ensures that semantic modularity exists for all such operations. So what I'm not showing you is the work about monad transformers and how they interact and how you can stack monads together. There's a thing in the Haskell community called the MTL library that uses that theory to allow you to reuse operations from lower down in the stack, higher up in the stack. And those proofs had to be done sort of handcrafted for each of the operations that were in play. But actually, all of those operations were algebraic, and so those proofs were not needed. They were automatically defined or automatically derivable from this property. Yes, this is how the lift operation works in the monad trans library. So that's first order effects, and they all obey this algebraicity law, which makes them behave very nicely. But then there are these things called higher order effects that contain scoped things. So they don't obey this law at all. So for example, if you have this program catch PQ, so the idea here is that catch runs the program P, and if P fails, so if there's a throw or an exception that happens in there, it will execute the program Q. And if you continue that combination of programs with K, that should not be the same as having K happen at the end of both of these programs. To understand why, consider what happens if K itself can throw an error. That would mean that if catch catch will succeed in P, everything goes just fine, and then K starts executing, and then something goes wrong. So part of K has been evaluated, and then an exception happens. Then we're going to execute Q, which recovers from things by executing Q, and then it's going to continue by executing k again, which means that the effects of k up to the failure have been repeated. And that's the problem with this law, where we don't have algebraicity at play here. So these are traditionally, in terms of the work by Plotkin and Pretnar, always implemented as handlers. And the reason is precisely because this algebraicity law doesn't work. But the problem is that this is a very serious limitation, because things like catch turn out to be useful in programs and useful as operations in their own right. So this is something that I discovered with Schreibers and Hintze in 2014, and we said, well, look, it's not enough to just consider algebraic operations. We need to have things like catch in our programs as well. There needs to be a denotational semantics for those too. So this catch is obviously a useful program. So that's where the idea of hydro effects came in. And for example, we can think of except as being an exception handler that deals with the catch operation. And this departs from the traditional first order world. So in the first order world, we think of catch itself as being a handler. And here I'm saying catch is an operation just like everything else. And there's another handler on top of that that deals with the catch effect. And it does so by wrapping the pure values in some maybe. And so things like exceptions and states should be able to combine in sort of natural ways. So one thing that we might want to do is fuse these two operations together. In order to do that, we start with a program that has throw, catch, put, and get. We pass it through this handler that removes the throw and the catch into a program where the pure value has maybe the result that we want. And then we pass this program through this machine that gives you back no more effects to handle. The state is maintained, and we have maybe the final state. So we would call this the global state, because we get to see the state globally after the computation has executed, whether or not an exception has been raised. So we can see that this is going from this program that contains all these different effects to a program with no effects and the state with maybe the pure value. But what happens when we flip these two different handlers round? So what happens when we have a different ordering to them? Well, something different occurs. You start with the same program, you pass it through the machine, and the state gets annotated. And we've removed put and get, and then we pass it through this machine, and this time we end up with maybe the state together with the pure value. And so this is a notion of what we would call local state, because if something goes wrong, you don't get to see the state. The whole thing is terminated. Okay, so notice that the handlers are not always commutative, and reordering them can have a change in semantics. And this has something to do with the interplay between the algebraic laws, but also it makes the higher order theory very difficult to deal with. So we dealt with this using what we call families of algebras parameterized by algebras. And the idea there is that when you define an algebra, you should have algebras as your input as well. So those input algebras are other effects that you don't know how to deal with yet. And when you pass, when you give an algebra to syntax that's higher order, you use those external algebras in the right place to give a semantics. And that's a technical detail that I don't want to get into. But the code that I've been presenting has been all inspired by this paper that we wrote last year. Okay. I think something's gone wrong. Okay, that's funny. My talk is out of sync with what's going on in the projector. Yep. So an exception was raised. Okay, thank you. I'm still out of sync, I think. I think I'm seeing something different. Well, I am seeing something different. Well, I'm winding up anyway. So let me just finish up. What we've seen here so far has been basically a tour of all the different modularities and high-order effects together. And I wanted to end with a slide that shows us what we started with, which was this SEO Trott quote, to ask ourselves, what has the tortoise taught us? And what the tortoise has taught us is that research is done over a long period of time with lots of small contributions without necessarily knowing exactly where everything is going to end up or exactly knowing how everything is going to be defined formally right now. And I think that should inspire us to carry on doing what research we have to do right now, no matter how small those steps feel. Okay, thank you very much.
You plenty exception. I hope it doesn't happen too often. Yeah, and we have plenty of time for questions.
Oh.
So you showed two ways to combine state and error handling,
Yeah.
but which corresponds to two different orders of your higher order handlers. There's actually a third way where the state is not thrown away on an error, but it's backtracked.
Oh, yeah. Yeah.
And is there any? Does this correspond to a combination of some simpler handlers, or is it kind of a monolithic handler anyway?
So yeah, good question. Backtracking state, I think, comes out very naturally when you deal with non-determinism. So non-determinism, instead of exceptions, can be one of the effects that we play with in here. So what you can do is have a handler that deals just with non-determinism, which basically takes your pure input and then translates that into a list of possible worlds. And then the way in which you do state versus the non-determinism handler will exactly give you either backtracking or non-backtracking state. So those two things come out very naturally from that. Yeah. I can probably say more, which is that I've got lots of nice examples of higher order operations on non-deterministic programs. So one of the higher order operations that you might want to do on a non-deterministic program is change your search strategy. So one of the things that we do in Prolog is the cut operation that kills off all the siblings to the right. But actually you can think of that as having a scope, which is the program that you want to influence under. And you can think of cut as being a search strategy that is sort of killing off everything to the right. You could change that search strategy and make it, for instance, to do depth first or depth bound or breadth first searches. And so this way of working means that you can annotate your program with sort of search scopes that say under here I want to search, and then you can have handlers that have sophisticated search mechanisms that you can change after the fact. So you have a single program and you decide, well, I want to get all the solutions, or I want the first solutions, or depth first, etc., etc. Yeah.
Further questions?
Thank you. So you didn't mention type and effect systems in this talk. So do you think they played a role somewhere in this development?
I do, and I did mention them in brief in that there was this, there is a fork near the beginning of the literature where initially type and effect systems come into play and have nothing to do with monads, and then that kind of goes off into that direction. So yes, there's an interplay there. I think monads is just another facet of the same problem, really. Yeah.
So I think this is kind of a troll, but there's a very nice early distinction, right? We have effects, which are first order and so forth, and we have handlers, which are higher order and so forth. And you say, well, no, but that's okay, because catch can really be treated as an operation, right?
Yes.
So at some point, isn't handle then just an operation?
Good question. I don't know how to do that. So call CC we can deal with, that's okay. But handle itself needs to deal with all the higher order operations, and there's some recursion there that I don't know how to deal with. So perhaps, I don't know.
Hi, I was curious, so this is all done in like kind of an intuitionistic setting. So how does linearity change like how we approach effects and handlers?
Yeah, so that's a great question. Depending on who you talk to, there are different ways of doing effect handlers. There are single-shot handlers and there are multi-shot handlers. Multi-shot, which basically don't accept linearity and say that you can resume a different continuation multiple times. If you insist on things being linear, then that means that things like backtracking for non-determinism is no longer possible. But it does mean that you can have much more efficient implementations of these things. Because you know that you're going to completely consume the continuation as you go through. So there are some really nice implications there from a practical perspective. I don't know if that answers your question exactly, but it's a super important part.
I was actually thinking of things like quantum programming where I was thinking of things like quantum programming where the linearity in the effectful operations is also important.
Okay.
Are there any other examples like that?
So where linearity is concerned, we do things like mutable state type things where we know we can mutate the state in place and everything works out nicely, which I'm sure you know about. That can be dealt with in this framework as well. I don't know about the quantum side of things, but yeah, I think it's a super relevant aspect of this. It's not something that I insist on in this particular library, but it's certainly something in the design space that we could insist on.
Okay, so hopefully a less trolly question. You mentioned fusing handlers.
Yes.
So each of these handlers you can kind of think of as a tree traversal.
Yes.
When you fuse handlers, does that lead to also sort of fusing tree traversals? So you end up with only one or fewer traversals of the original syntax tree?
Yeah, that's exactly right. And we wrote a paper about that a few years ago that says exactly that fusing different handlers corresponds to fusing traversals, so you can, instead of doing multiple passes over the tree, you can do a single pass that does all the work at once. And actually that is critical to the way this all works. Yeah.
So you talked in the section about modularity, you talked a lot, I think, about, we've had a lot of success in, handlers have made things, have made it easier to build up larger things from, larger semantics from smaller ones.
Yep.
But another aspect of modularity that we think about in software design is encapsulation. With handlers, that problem isn't entirely, with sort of handlers as they're originally formulated, that problem isn't entirely solved in the sense that you might invoke an operation whose semantics leak into another handler that's installed by a program that's out of your control. So, where do you think we are?
Yeah.
Broadly with this, this encapsulation part of modularity.
Yeah.
What's next, or what do we need to do?
That's a great question, and I think that this framework works quite well with respect to encapsulation. So, with encapsulation, we want this idea that you know about all of the side effects that are going on, and there's nothing that escapes that control. And in my Christmas tree slide, at the bottom, you have the effect on what it does to the pure values. That's the thing that precisely says what the entire scope of this of the effect is, and how things using monad transformers. And those monad transformers fully describe the denotation of everything that could be changed. So there is no leaking going on whatsoever. I haven't shown you, but examples that we can do in this library are things like effect hiding. So we're able to make the handler not see various effects. And that's a nice demonstration that the encapsulation is working perfectly well. So you're able to hide certain operations that that handler would normally see, and then they don't get touched at all by the handler. So that sort of demonstrates that there's no leaking going on at all. So I think this is dealt with. Yeah.
Hi, I have one more question. You said something very interesting a few moments ago. You said you could fuse these tree traversals.
Yes.
And if I just think about FNG tree to tree, like if you want to fuse them, they both have to traverse the tree in the same order, like both pre-order or both post-order. Does that always happen with handlers? Like, do you always traverse the syntax tree in the sort of the same?
Yes and no. So yes, you always traverse the tree sort of in a top-down fashion. But there is the so-called rep-min problem, which says that suppose you have a tree of values and you want to replicate the minimum value in that tree. So you might be thinking, oh, well, the only way to do that is to traverse it twice. You have a traversal that finds the minimum, and then you traverse again and propagate that minimum everywhere. But actually, that can be done in a single traversal, which traverses the tree and creates a kind of continuation structure that says, when you find out where the minimum is, please insert it into this function, and then you can traverse the tree, creating this continuation structure and finding the minimum at the same time. And once you've finished traversing the tree, you're left with a big function and the minimum value, and you apply that function to the minimum value, and that propagates through. That repmin trick is what allows you to have alternative traversal structures through your tree. What you're doing is you're traversing through your tree, creating a continuation structure that does the traversal that you really want, and then at the end you can kind of hit that with a value that then does the traversal of the tree in a completely different way. It's a kind of a cheeky answer, because we did traverse the tree once, in the sense that we traversed it and we created a continuation structure. But it's all cheeky because we're about to then follow that continuation structure, which goes through the tree again, right? Yeah. Although it's not the tree, it's now the continuation structure. So that's why it's a sort of technically we've been through the tree once, but in practice we're going to do some pointer chasing afterwards. So, yeah.
Okay, thanks.
Sorry, can you just make sure that you can switch slides now?
I don't think I'm seeing this slide at all.
Okay. Further questions? Is it, maybe I have one. It's long ago that I programmed Haskell, but what you showed, is it mostly about Haskell, or is that in general about programming?
Yeah. I presented a library that's implemented in Haskell, but these ideas far exceed Haskell. So there are implementations in OCaml, in C, in, I think, JavaScript, and all sorts of different things as well. So the concepts, I think, are really nicely explained in Haskell, because you can't play tricks on the type system, and you have to be upfront about everything being interpreted by a monad transformer. And that drives us to be very accurate with the theory side of things, whereas if you're doing this in OCaml, the type system can get sort of put to one side, and then you can do all of this stuff by just not typing all of your effects and not working within a monad, or at least, sorry, not explicitly working with a monad. And so that turns out to be very good, because it means that we can implement these things and they work well. But from a semantics perspective, it's not exactly clear which monad we're working in now. In a sense, it doesn't matter, but from a theory perspective, I want to know. So that's why we do it this way.
Okay, and say if you have this theory and a framework that is able to explain all this, is it in the first place for proving properties, or being more efficient from the execution side, or for the user to write better code? What's the...
Yeah, the motivation for me at least is, it seems to be working now. The motivation for me at least is to have Haskell programmers be able to write code that works, that uses effects. There is something called the MTL library, and that does that perfectly fine, but it's restricted to exactly a particular set of operations, and extending that beyond that requires work on proving various properties of things. This framework allows you to add new operations without that proof obligation. And so, in that sense, it's more modular.
Sounds great. Okay. There are no more questions. Now, due to this interruption, we are slightly ahead of time. And let's thank the speaker again for this great talk.